Welcome to another theorem from Real Analysis 4. This is the first actually difficult theorem on the channel actually. So let's get straight to it. It's the theorem T13.4, limit derivative exchange theorem. Okay, without any further delay, let's get straight to it. Let fn be some sequence of functions ranges through 1 to infinity. Be a sequence of finitely differentiable functions on the interval AB, which is some real open interval, and let the following two criteria hold. Alright, the first. Assume that there exists some number x0 from the interval such that the sequence fn converges, fn of x0 converges. And number two, assume that f prime, or the derivative of fn with respect to x, converges uniformly locally on the interval AB. Then, if these two criteria are met, then there exists a function f such that fn converge locally uniformly to f on AB. F prime is finite. So we assume that the individual members of the function sequence to which converges to f, that they are finitely differentiable. Well, the function that they converge to is also finitely differentiable. And so that's a property that's preserved. And fn prime converge also locally uniformly to f prime on AB. Okay, so these are some pretty strong claims, so it makes sense that the proof is non-trivial this time. Well, without any further ado, let's get to it. Let CD be some subset of the interval AB. We will essentially prove convergence on this closed subset. Because, by definition of local uniform convergence, it is sufficient to show uniform convergence on any arbitrarily chosen closed subset, which is what we will do. So, by proving uniform convergence on this CD, because it is arbitrarily chosen, we shall prove local uniform convergence on the whole AB. And x0 be an element of the interval CD. No, so it's not an endpoint. We know that fn converge uniformly on CD. This is by assumption. But what we want to show is that they converge specifically to f. then we will get uniform local convergence to F on the whole AB. So we wish to show that Fn converge uniformly locally to F on CD. Alright. Pardon me. We want to show that they converge uniformly on CD, and then we will get local uniform convergence on AB. Sorry about that. And how else could we begin than by choosing some epsilon greater than 0? That's always a good idea in analysis. Now, since Fn is uniformly convergent on CD, we get, by the Bolzano-Cauchy criterion for uniform convergence, or BCC2 for short, that there exists some n0, or I will highlight the used theorem in blue. We will get that there exists some n0 such that for all natural mn greater or equal to n0, and for all x in the interval CD, we get that f prime n of x minus, well, and fm prime of x are close. Oh, and pardon me, of course, here it's fn prime. We know that this uniformly converges by the second criterion. That was that was a typo. Now, also we assume that for all m, and well, by rather the classical Bolzano-Cauchy criterion, we know that for all mn greater or equal to n0, again, we know that there exists some n1 for which this would be true. We know there exists some n2 for which what I'm writing would be true. We take the maximum of both, and thus we have one n0 for which both of these statements are true. For all n greater or equal to n0, we have fn of x0 minus fm of x0 is smaller than epsilon. Alright, what next? Well, now, for all x in CD, fn of x minus fn of x is, and we shall now use the triangle inequality, and we want to show that it is small. So we shall be using the Bolzano-Cauchy criterion for uniform convergence here. That's why you have for all x on the left-hand side here. And if we manage to show that this is smaller than some epsilon, then we shall know that fn uniformly converge to f. Well, at least on the closed interval CD, and then by extension locally uniformly converge on the whole AB. We shall divide this bracket in an unusual way. So we will have here fn of x minus fm of x, and now minus some garbage plus fn of x0 minus fm x0. And the same thing we put in here. The reason why we do this sort of strange division is to get precisely this term out, because we have a good estimate for it. We know from here that it is smaller than epsilon. Oopsie. It is smaller than epsilon. Now, I shall copy it here as well. So here we have bracket fn of x0 plus fm of x0 plus the remaining bit. Okay, well, now fix an m. Put h of x equal to fn of x minus fm of x. That's a reasonable choice because it occurs quite a bit in these two brackets, well, in these two absolute values. So we define a new function h, and using the h notation, we will get the argument of this absolute value, which we still need to estimate, is equal actually to what? To h of x minus h of x0. Yeah. Okay, but we can use the Lagrange mean value theorem, which we absolutely can do because the Lagrange mean value theorem only assumes that the function in question is continuous on the whole interval and that the derivative exists everywhere, where we have finite differentiable function. So A, it is continuous, and B, it is differentiable. So we can use it, and after we do, we obtain the following equality. So we will get that fn of x minus fm of x is smaller or equal to than x minus x0 times f prime n of some xi minus fn prime of some other xi plus epsilon. Of course, it's an m here. But whoa, what a dump. Well, how did we get to this? It's quite simple. We basically took this from here, then we estimated the second term here by epsilon, that's this epsilon right here, and then we applied the Lagrange mean value theorem on this middle term. And what happened? Well, this is the difference of the arguments, which, well, that's the standard form, almost standard form, and this is the derivative of h at some values I. So, quite simple, quite straightforward. What do we do now? We were very clever, and we know, actually, that this bit is smaller than epsilon from up here. Alright, well, that's good news. Because this bit up here tells us that these two functions, well, their derivatives, are smaller than epsilon for all x from the interval. And xi from the Lagrange mean value theorem is from this interval. So, shamelessly, we can write that this is, that this is equal to x minus x0 of some epsilon plus some epsilon. Well, okay, but this is bounded because we are dealing with x from a bounded interval, and x0 is also bounded. So this is definitely smaller or equal to, this is equal to or smaller than the length of the interval times epsilon plus epsilon, which is precisely what we wanted. So we have just now shown that Fn converges uniformly to f on CD. And since CD was chosen arbitrarily, this means that Fn converges uniformly locally to f on AB. Well, that's good news. That's a major part of the proof finished. Well, we're not quite done yet. Now, part 2, which is a little bit worse, but it's not terrible. It's not bad. It's manageable. We're strong, can do it. So, it still remains to show. So, we still need to show, or rather, we wish to show that Fn derivative converge locally uniformly to f prime. Well, again, we shall show that fn prime converge uniformly to f prime on the closed interval CD. And if we prove this, the claim will follow. Alright, well, what do we do? Well, we begin by defining a new function. So put a new function, call it script s, of n of x, and we define it as fn of x minus fn of z over x minus z. And an observant listener or viewer will note that we are setting this up essentially for the limit as z approaches x, or rather as x approaches z, and we will get the derivative of fn. Well, alright. Well, like this, we will take n to infinity. Well, this stinks of the previous theorem that we have proven, that being the Moore-Osgood theorem, and indeed we shall use it. Very well. Enough talk and more action. Now, for x from the interval without that. Alright, well, we wish to show the assumptions of Moore-Osgood theorem hold. How shall we do it? Well, first off, by letting epsilon being greater than 0, that's a good idea. By the Bolzano-Cauchy criterion for uniform convergence theorem, there exists some n0 for all n greater or equal to n0 for all x in the interval, such that fnx prime and fmx prime are close. They are small. Their difference is smaller than epsilon. Well, fine. Now, similarly to what we did in part 1, what did I want to say? That similar to what we did in part 1, we take fn of x minus fm of x minus this monstrosity again, fn of z minus fm of z. And again, using the Lagrange mean value theorem, we find that this is actually equal to the difference of the arguments times the difference of fn of xi minus fm of xi, or in other words, the derivative of some function h at xi, right? And but we have an estimate for this, right? By the where are you? Up here. Result for all x in CD specifically, in particular it will work but for xi from this interval. So by this estimate up here, we will get that this is smaller or equal to x minus z times epsilon. Nothing clever. Alright, well, we put before, during this step, h equal to fn minus fm. We're going to do it explicitly now. And now for all nm natural greater or equal to n0, we will have that for all x in CD, barring z, for this we evaluate what script s n of x minus script s m of x is smaller or is equal to, and it is equal to, by definition, to fn of x minus fn of z, we move the terms around a bit, minus fm of x minus fm of z. I mean, bollocks, we don't even move the terms around. This is precisely the definition. Now, divided by x minus z, that's the common denominator. And we, however, have an estimate for this. We know what this is. Although, of course, my instincts were right. We're going to be moving the terms around because this is equal to the following fraction. We'll have x minus z in the denominator. And up here, if we move around the terms, we get fn of x minus fm of x. Then we get minus bracket, and then what? Fn of z minus fm of z. Does it check out? Yeah, of course it checks out. And now magic happens, because this is precisely this up here. Correct? And as such, we have an estimate for this. We know that this is smaller than, or strictly smaller than, sorry, here should have been just smaller than. We know that this is smaller than x minus z bracket times epsilon over x minus z. Well, this is just epsilon. So we have thus verified the first requirement of the Moore-Osgood theorem. Namely, we will be using the Moore-Osgood theorem on script Sn. Alright, and the first requirement is that they converge uniformly on the given interval, which we have just now demonstrated, because the choice of x was free, and we have shown that the difference of script n x and script n m for any n m is small, well, greater than some n 0, doesn't matter, and thus by the Bolzano-Cauchy criterion for uniform convergence, we have that script s and converge uniformly on the interval CD without z. Alright, but we are also, the Moore-Osgood theorem supposes that we are working on a singular interval, which is not entirely true here, because we are not working on an interval, we're working on a sort of split interval. But we are verifying the assumptions on both subintervals, both the subintervals CZ and ZD, right? And D is the endpoint of the interval, which is assumed in the Moore-Osgood theorem, and we can approach it from either side because we are working with both subintervals. We are proving the theorem for both subintervals at the same time. Also, I would like to point out that we do not explicitly say what script Sn converges to. It is sufficient to say that it exists, because we actually won't be using it afterward. It doesn't actually even appear in the claim of the Moore-Osgood theorem besides the assumptions. In the actual body of the theorem, it doesn't appear, or doesn't have to appear. Alright, but we're not finished quite yet, because we still need to verify that the limit as x approaches the endpoint of the interval, which in both cases, we are working with two subintervals, but in either case we are still working with the endpoint being z. And we need to show that this limit exists and that it is real. So let's do that. Very well. So, taking the limit as x approaches z, of script Sn of x. Well, what is this? Well, by definition, this is the limit as x approaches z of fn of x minus fn of z, using the definition of s script here, over x minus z. But this is the definition of a derivative. This is by design. This was no coincidence. We designed script s for this to occur. So quite cleverly, we see that this is actually equal to the derivative of fn at z. And we know, well, by assumption, we have that the sequence is finite differentiable, and therefore this derivative is also finite and real. Alright, so we have verified, or we have checked the assumptions of the Moore's good theorem. Alright, but what next? Well, it's quite straightforward actually, because applying the Moore's good theorem, we have that by Moore-Osgood theorem, we have that the limit as n approaches infinity of the limit as x approaches z of phi n, script s n of x is equal to the limit as n approaches infinity of the limit as x approaches z of, by definition, fn x minus fn z of x of z x minus z. Now here comes to play the Moore's good. This is equal to, we swap the limits, we will have limit as x, the limit as x approaches z of the limit as n approaches infinity of fn of x minus fn of z over x minus z, which is equal to, for completeness, the limit as x approaches z of the limit as n approaches infinity of script s of x, script sn of x. Okay, but this is brilliant actually, because if we just focus on this bit in the middle, we are essentially finished. Because what this is in essence saying is that the limit as n approaches infinity of the derivative of f n at z, because this is the definition of a derivative, is equal to the limit as x approaches z of f of x minus f of z over x minus z. But this is just, again, the definition of a derivative. This is the derivative of f at z. We have used here that f and converge to f, which follows from the fact that f and converge uniformly to f on the interval CD. So it just remains for us to combine two little quaint facts, and we are finished finally. So consider, just to mention, this is by the previous section. Consider that fn prime converges to f prime, and at the same time we know that fn prime converge uniformly. Well, fn converges uniformly, and fn prime converges uniformly, and fn converges pointwise, or fn prime converges pointwise to something. Well, then this must converge to the same value. You cannot have a function pointwise converging to another function and then uniformly converging to another function. That doesn't make any sense. So we have that Fn prime converges uniformly to F prime on CD, and thus Fn prime converges locally uniformly to F prime on our original interval AB, which concludes the proof. Ha!